I'm going to describe the purpose of a stripping column and then show the mass balances and then how we use those to calculate the number of equilibrium stages. I'll show a graphical approach. Let's look at the idea of a stripping column. We start with a liquid that has some concentration of solute that we'd like to decrease. And indeed, in this example, we go from 0.35 parts per million down to 0.11 parts per million. And we do that by contacting it with vapor. The gas has a low concentration of that solute, and then it leaves with a much higher concentration. And if we look at the overall system, we can see coming in the liquid phase, if we multiply the parts per million times the flow rate, coming in is 35 moles per hour in the liquid phase, and leaving in the liquid phase is 11 moles per hour. So that says we've removed 24 moles per hour. And if we look at the gas phase, we go from 1 part per million to 25 molar flow rate times the mole fraction. Indeed, we have a steady state mass balance. We have now added 24 moles per hour to the vapor phase. And you can see in this 5-stage example, the mole fraction increases in each stage. So one of the important numbers in the calculations you're going to do is the liquid to the vapor flow rate, and for this case it's 100 over 1. And other important thing to keep in mind is our notation xn, yn. These are two compositions, two phases of equilibrium. In other words, if I write x3 and y3, that means leaving stage 3, the liquid mole fraction is xn, the vapor mole fraction or mole ratio is yn. Those two are in equilibrium. Now the equilibrium we're modeling by a Henry's law because of low concentration. So Henry's constant over pressure times xn. So in this case, Henry's constant has units of pressure. So what I'm going to do is pick 3 stages and we'll do a mass balance around here. And what that means is if I look at what's coming in for the solute, it should equal what's going out. So what's coming in is x0 times liquid flow rate plus into stage 3 is y4 times the vapor flow rate. What's leaving then x3 times the liquid flow rate, y1 times the vapor flow rate. Well, in general, I could write this as, remember this was stage 3, so that's n plus 1. This is xn times L, y1 times v. This forms the operating line, so let me rewrite it in terms of y versus x. So to determine number of stages, I'm going to use a plot of y versus x. This is the operating line on that same plot. This then will be the equilibrium line. So let's look at a plot and put some numbers in just to give you an idea how to determine the number of stages. So in this plot, here's the equilibrium line, here's Henry's law, and this is the operating line, the mass balance. So I'm going to just use some numbers just to demonstrate. So I used an L over V in order to generate this plot of 81.7, and we'll use x0 as 0.35. And let me remind you the notation y1, and let me write the rest of those down. So if I locate the starting point, 0.35, the mass balance, then here would be x1 and y1. And then I would step through using the mass balance and equilibrium, so x2 and y2 from the second stage. And I'm doing this by hand, but certainly be more accurate with a ruler. I just want to demonstrate the idea of stepping through. So this is stage 4, and then here is stage 5. So x5, y5, and then this would be y6. Right, so this is the bottom of the column, and this is the top. And of course, I picked numbers to make this come out nicely, but this says that x5, what's leaving now, is about 0.13. So we decreased solute from 0.35 to 0.13. It's the idea of a stripping column using a gas to remove some solute from a liquid phase.